Good afternoon. Section 7.8. Indeterminate forms and L'Hopital rule. Okay, so this is a French guy, and this is not hospital. Okay, not hospital, L'Hopital. So that's how we say it. Please remember this. No hospitals. So to motivate, I will start with the following function. Okay, and let's suppose that I want to take a limit as x goes to 1 of this function. So it's the limit as x goes to 1 of log x divided by x minus 1. So you can see that, of course, when x is equal to 1, this function is not quite defined, because the denominator simply turns into 0. What happens to the numerator at 1? It also turns to 0. So it's a very strange limit. We cannot write down that this is the limit of this divided by the limit of this, because this one doesn't, this is 0. So we could not use that simple rule. So something else happens there. And this kind of limiting behavior is called an indeterminate form of type 0 over 0. So let me start my log here. Indeterminate forms. So this is an indeterminate fraction of type 0 over 0. Okay? When x goes to 1, the numerator goes to 0, and the denominator goes to 0, and it's not clear what the resulting limit is going to be. So the denominator wants to turn this fraction into 0, because the log tends to 0. But the denominator is also tending to 0, so it wants to make it really large. So we have a certain struggle. The numerator wants to make it as small as possible. The denominator wants to make it very large, infinitely large. So who's going to win is not clear. Okay. Another one. We're going to look at the same function, actually, but we take x to infinity. So this is the limit as x goes to infinity of log x over x minus 1. What's that equal to? Well, let's look at the numerator. What happens to log x when x goes to infinity? It goes to infinity. Remember the graph of log? Okay, so it goes to infinity slowly. How about the denominator as x goes to infinity? That's also going to infinity. So as x increases, the numerator increases, wanting to make this fraction very large. The denominator also increases, trying to make it really small. Who is going to win is not clear. So here we have an indeterminate fraction of type infinity over infinity. I'm going to put it here. Special fractions like this require special treatment. Okay? In order to evaluate these limits, there is a method called L'Hopital rule. Okay? That we're going to learn now. So let's first put down the theorem. Suppose f and g are differentiable g prime of x is not 0 on an interval I. Okay? That on an open interval I that contains A. So we are going to look at the following limits. Let's suppose that as x goes to A, so A is some number, okay, on our interval. Let's suppose that this function goes to 0, and the second function, g of x, also goes to 0. Or, okay, it's, the limit of x is plus minus infinity, and the limit of g is also plus minus infinity. Okay? So this one gives me 0 over 0. This gives me infinity over infinity indeterminate form. Then we have a simple and very useful rule to evaluate the limit as x goes to A. So we form the fraction of f and g. Okay? And in one case, in the case outlined in the first line, we get 0 over 0. In the case outlined on the bottom line, we have infinity over infinity. The way to deal with this is the same. This is the same as the limit as x goes to A of the two derivatives. Okay? So if we don't know how to evaluate the original limit, we take the derivative of both the numerator and the denominator, and that gives us the correct value for the limit. First, I'll give you some examples, and then I'll explain why and how this works. Okay? So the first example is going to be the one we already looked at. So the limit as x goes to 1 of log x over x minus 1. So you see that the numerator goes to 0, the denominator goes to 0. So here we can put in quotation marks 0 over 0, right? What's the next step? We take the derivative. According to L'Hopital's rule, we take the derivative of both functions. So it's the limit as x goes to 1. What's the derivative of log? 1 over x. And the derivative of x is simply 1. Okay? And can we take this limit? Yeah, this is really easy, right? It's 1 over 1. So like magic, it turns this indeterminate form into something that is simple and easy to evaluate. Okay? Another example. Let's look at this. X cubed over e to the x. Why does this belong to the class of indeterminate fractions? When x goes to infinity, the numerator tends to infinity. It grows indefinitely. And the denominator also does the same. We have to determine which one approaches infinity faster. This is the one that's going to win. Okay? So what we need to do is to take the derivative. So the derivative of the numerator is 3x squared, and the exponent stays the same. Okay, now what? The limit of the numerator is infinity. The limit of the denominator is also infinity. So we're again facing an indeterminate fraction. But you see it's a little better because the power has gone down. So let's keep doing it. This is the limit as x goes to infinity of 6x over e to the x. Another indeterminate form. But this one contains only the first power of x. So only one more step separates us from the answer. So we have 6 over e to the x. Is this an indeterminate form? No, because the numerator is 6. It's a constant. It doesn't go to infinity. The numerator goes to infinity. So what's the answer? 0. Okay. So this indeterminate form, here the numerator wins. Why does it win? Could we tell right from the start? So see, on the top we have a power function. At the bottom we have an exponent. Which one grows faster? The exponent. The exponent grows faster on any power. Okay. So it forces the whole fraction to go to 0. Okay. Questions? Let's look at this limit of log x over square root of x. Okay, so the numerator is infinite, the denominator is infinite, so here we can put infinity over infinity and take the limit. So 1 over x, and we have to differentiate square root. Okay. So now, if we don't do anything else, we see, oh, this goes to 0, and this goes to 0, and so we have another indeterminate form. But in fact, we don't have to do this, because at this stage we can simplify by turning this thing over. Okay. So let's just rewrite it without further differentiation. Okay. This gives me 2 square root of x divided by x. And we can simplify further. 2 over square root of x. What's the answer? 0, because it's 2 over square root of x. X goes to infinity. The answer is again 0. Okay. Next one. The limit is x goes to 0. Am I going too fast? No. Tangent of, not this one. Sine x minus x over x squared. Okay. All my examples, most of my examples are different from the textbook, so you have twice as many. At the numerator, we have 0 minus 0, so that's 0. Denominator gives me 0, so we have 0 over 0 here. We take the derivative. So when we differentiate the sign, we get cosine minus 1. And here we have 2x. Now we look at this one. As x goes to 0, cosine goes to 1. So we still have 0 in the numerator, and we still have 0 in the denominator. Do it again. Again, 0 is 0. So limit as x goes to 0 minus sine x over 2. What's the answer? Now it's 0. It stops being an indeterminate form at some point, and we can simply evaluate the answer. Okay, let's do some more. By the way, I'll break this down a little bit. I want to show you why it works, okay? Why does this magic work? So the full proof of L'Hopital's rule is not easy. It's especially hard in the second case, infinity over infinity. And it's slightly easier for 0 over 0, but I won't even do that. I'll just show you a specific, simpler instantiation of this proof. So suppose that f of a and g of a is equal to 0. Okay. F prime and g prime are continuous. And g prime of a is not equal to 0. These are some restrictions that I impose to make my proof simpler. Many of them break down. Like, for instance, here. So this is f. This is g. When we differentiated g, we got 2x. That's 0. So this proof would not hold for this particular example, but it holds for many more. Okay? So we want to show that the limit f over g is equal to the limit of the derivatives. So I'm going to start from the right and go to the left. So I'm going to write the limit as x goes to a, f prime over g prime. Okay. Now we can remember the definition of derivatives. X goes to a, f of x minus f of a, x minus a. That's the derivative of f evaluated at a. Now here, the derivative of g evaluated at a. These are definitions of the derivative. So we have, oh, I'm sorry, I forgot to put here a limit as, no, it's okay. Everything's good. So we have the limit on top and the limit at the denominator, okay? And now we can actually replace it with only one limit and write down this double story fraction. X minus a divided by g of x minus g of a, x minus a. And of course, you can see that these two things cancel. Okay? So I have the limit as x goes to a, f of x minus f of a, g of x minus g of a. Now we go back and we see that we assume that both f and g were 0 at a. So this simplifies even further. This is 0, and we have limit f of x over g of x. So I proved exactly what I wanted. I went from here to here. Okay? I showed that the limit of the derivatives is equal to the limit of the fraction of the functions themselves. Okay? So let's follow with a couple more examples. Let's look at the limit of tangent 3x over x. So a trigonometric limit. This is 0 over 0 because the tangent of 0 is 0 and x also is 0. So we take the limit. What's the limit of the tangent? It's 3 divided by cos squared 3x. Okay, divided by 1. Now x goes to 0, cosine goes to 1. So what's the answer? 3. Very good. The next example is going to be wrong. Okay, write it down. Don't do this on your own. Let's calculate the limit as x goes to 0, cos x over x. Okay. So what I do here, I take the limit. The derivative of cosine is minus sine. The derivative of x is 1. And what's the answer? Is 0. Now go back. So what's my original question? I have a cosine, which is quite innocent at x equals 0. It goes to 1. And I divide it by 0. And for some reason, I got 0. How can this be? What is the mistake? Can you see this? So cosine of 0 is a function that approaches 1. So I take something that is around 1, and I divide it by 0, and I get 0. Where's the mistake? It's not an indeterminate form. So this is not an indeterminate form. And if you do apply L'Hopital's rule without having an indeterminate form, you'll get the wrong answer. It only works for these, okay? It only works for the indeterminate forms. And this demonstrates very well that if you apply it outside its area of applicability, it simply leads to a wrong answer, okay? So this tends to 1, this tends to 0, and the actual answer here is infinity, okay? So this is equal to infinity. Okay. Okay. Now I want to add the next animal to our zoo. Indeterminate product. Okay. So as an example, let me show you the following. Limit as x goes to 0 plus of x squared log x. First, let me ask you, what is this notation? X goes to 0 plus. It's the right limit. It means that x remains positive as we go through the limiting process. Okay, so what happens to the two components here? This guy goes to 0, obviously. How about the log?
0.
It goes to, what happens to the log? F as x, so this is x, this is log x. What happens to the log when x approaches 0 on the right? Negative infinity, exactly. And now you can see immediately why I had to say 0 plus. 0 minus, that would be a limit coming from here. There is no log here, right? I could not approach this 0 from the left. I have to approach from the right for the sake of the log, okay? So we have two terms multiplying each other. This one is trying to make this 0. This is trying to make it infinity. And you can see it's the same kind of contradiction, like pulling the rope. Who is stronger? And so this is called an indeterminate product of the form 0 times infinity. So we say 0 times infinity. And L'Hopital's rule doesn't apply here because we don't have a fraction. So what can we do? Well, the answer is very simple. Any product can be turned into a fraction by only one, in one line. So let's consider x squared log x. How can I make a fraction out of this? Well, I'm going to keep the log in the denominator, and I'm going to divide it by 1 over x squared. That's a fraction, right? It's the same thing, but it's a fraction. And now, what kind of fraction is it? So x goes to 0, so the log goes to minus infinity. How about 1 over x squared? Goes to infinity. So what we have is actually infinity over infinity. Right? So an indeterminate product of this kind will always turn into an indeterminate fraction of one of these kinds, one or the other. So simply we write here the same expression, but expressed as a fraction. And now we say this is infinity over infinity. And by the way, I don't care if it's positive or negative infinity. Okay, the L'Hopital's rule will hold for either one of them. And I don't have to say minus infinity over infinity. I can just say infinity over infinity. It's just a notation. So now what's the next step? Is to take the derivative. So on top I have 1 over x. And here I have 1 over x. Oh, I'm sorry. I took the antiderivative. So as before, we already had an example like this. We don't continue with L'Hopital's rule. We just simplify, right? At this stage, it doesn't make sense to consider this in a determinate form. It only gets worse if we continue to differentiate. Imagine differentiating this and this. That would become 1 over x squared. That would become 1 over x fourth. And this would be like a runaway process. So instead of that, we simplify. We say that this is the limit of 1 over x minus 2x cubed, right? Simplify some more. Minus 1/2 x squared, and that's 0. Okay. Question?
Where did you get the negative 2 under 1 over x?
This is a derivative of this.
And so that's 1 over x negative 2? Oh.
Right? Okay. Very good. So next, we are going to plot some function by using L'Hopital's rule. Okay. How can it help us visualize functions? Plot f of x given by e to the minus x over x. Okay. So let's draw the coordinates. This is like 2a, right? We probably did a lot of plotting there. So we have to find all sorts of asymptotes that this function might have. So let's first consider the limit as x goes to infinity of this guy. Oh, no, let's do that last. I'm sorry. First, I notice, because that's the central point. So first, I notice that this function is discontinuous at x equals 0. So we want to know what happens to the function when x goes to plus 0 and minus 0. So let's start with x going to 0 on the right, okay, of e to the minus x over x. So let's recall the properties of the exponent. What is e to the 0? 1. And the denominator goes to 0. So it's 1 over 0. So the answer is plus infinity. And I can draw it like this. Okay. Now, x goes to 0 on the left. Again, the numerator is 1. The denominator goes to 0, and it's negative. So the answer is minus infinity. So we have this discontinuity here, like this. Okay. Limit. Let's do it here. I need to know the plus and minus infinity limit. So limit as x goes to minus infinity, e to the minus x over x. So now we can see that we have an indeterminate form. Why? Because when x is negative and it goes to infinity, minus x is positive and it's going to infinity. So e to the minus x goes to infinity, and this goes to minus infinity. So it's infinity over infinity type thing. So we need to take the derivative. Okay, and now it's clear that the answer is minus infinity. So somehow this guy does this. And finally, we do the limit as x goes to plus infinity of the same thing. So what happens here? As x goes to plus infinity, what happens to the exponent? 0. It's a negative exponent, right? The negative exponent looks like this. It goes to 0 as x goes to infinity. So this is 0. And so we have 0 over infinity. That's not an indeterminate form. For sure, it's 0. So we have this the horizontal asymptote of this graph is 0. Okay, so in this graph we had to take 4 limits, and only one of them actually turned out to be an indeterminate form, which required the use of the L'Hopital's rule. Okay, very good. Next, we go to the third animal. This is called indeterminate difference. And here's my example. So the limit as x goes to 0 plus of 1 over sine x minus cotangent x. Okay. So first of all, do you remember what cotangent is? It's a cosine over sine x. So when x goes to 0 on the right, this guy stays 1, this is 0, so we have plus goes to plus infinity. Okay. How about this term? As x goes to 0, sine goes to 0. 1 over sine goes to plus infinity also. So we have a really, really large number, and we subtract another really, really large number. They're so large, they're infinite. Okay, so we cannot tell. Maybe there are different types of infinity, and if we don't know which one is bigger. Okay, so this is the nature of indeterminate differences, and they always have the form infinity minus infinity. Okay. It may turn out to be a finite number, or it could be 0, or it could be minus infinity or plus infinity. Anything is possible here. And for all of these and more, the only rule, the only method, really, is somehow to turn it into an indeterminate fraction. Because for indeterminate fractions, we have L'Hopital's rule. Nothing else works. So we have to use tricks to turn whatever we have in indeterminate form into an indeterminate fraction. So in this case, and it's probably, this is the hardest to give you a definite algorithm for. Each one of them is different. Somehow we just have to manipulate what you have. You have to manipulate this difference to turn it into a fraction. Okay, so in this case, what can we do? We rewrite it in terms of cosine and sine. Okay. And now, of course, we can see that sine appears in both terms as a denominator. So we have a limit of 1 minus cos x over sine x. So we got it to be a fraction. X goes to 0. So cosine goes to 1. 1 minus 1 is 0. And the sine is 0. So this is good. We got this difference. We rewrote it in terms of an indeterminate fraction. And now it's L'Hopital. So we have the limit of sine x over cosine x, okay, by taking the derivative, and this is 0. So it's quite interesting because we take a really, really large number, subtract another really, really large number from it, and they turn out to be exactly the same, although they are not, right? So, and the last type of indeterminate forms is called an indeterminate power. And there are 3 types of these, okay? 0 to 0, infinity to 0, and 1 to infinity. Okay. So why are these indeterminate forms? Let's think about the first one. Zero to 0. Let's suppose that I take 0 and raise it to power a. What do I get? 0, usually. Okay. Now let's suppose I take a number b and raise it to 0. What do I get? 1. Okay, so you can see that the base wants my power to be 0, and the power wants it to be 1. Okay, and there is a certain contradiction here between the two. Why do I even write it like this? Because 0 to 0 is just a notation. None of the functions that appear in this limiting process are 0. They are functions. They are functions of x. X goes to a, and the base function has the limit 0. The power function has the limit 0. But they are not equal to 0. So it's like having b to a when b goes to 0 and a goes to 0. Right? So, but which one goes to 0 faster? If this one reaches 0 faster, then it's going to make the whole thing 0. If this one reaches 0 faster, it's going to make it 1. Okay, so this is kind of the reasoning why this is indeterminate. It's much more sophisticated than here. Here I think it's pretty clear, like denominator, numerator struggling. Here it's a little bit more subtle, but still it's the same idea. So if you want to look at infinity to 0, okay, so infinity to number to a wants to be infinity, and number b to 0 wants to be 1. So it's a struggle between finite, 1, and infinite, infinity. And the last one is 1 to infinity. So what's 1 to any power? That's 1, right? And what is b to infinity? That's, well, it depends. Because if b is greater than 1, then it's going to be infinity. If b is smaller than 1, it's going to be 0. But it's never 1. So this one wants to be 1, and this is 0 or infinity. So we have the contradiction. Okay, fine. So let's look at some examples of this. We have the limit as x goes to 0 on the left, 1 plus sine 2x to the power of cotangent x. Okay, so x goes to 0. So the expression in brackets, as you can see, goes to 1. And the cotangent, we just looked at it, it goes to infinity. So this is, I'm sorry, so this is 0 minus, okay? So let's look at the limit. 1 plus sine 2x, 0 goes to, that's 1. And the limit of cotangent x, when we approach 0 on the left, it's 1 divided by, it's cosine, which is like 1, divided by sine, which is like 0 with a minus sign. So it's minus infinity, right? So this indeterminate power is of the type 1 to infinity. Can you see this? So how can we solve this limit? The rule is always the same. Try to make this into an indeterminate fraction. There is no other rule. Okay, that's the only form for which we have L'Hopital's rule. So how can we turn this into an indeterminate fraction? So there is a method, fortunately, to do this. let us denote the method take the log. Okay, so let's denote as y this whole object, 1 plus sine 2x to the power of cotangent x. And then take log of y. So this is the log of 1 plus sine 2x to the power of cotangent x. Do you remember what happens to the power when we take the log? The power goes here, right? So we have cotangent x times the log of what was there. Okay. So, and we are going to work with this quantity now. We want to evaluate the limit of the log. Okay. So what is the limit as x goes to 0 minus of cotangent x times log 1 plus sine 2x? So as x goes to 0, the cotangent goes to minus infinity. And we have sine disappears, so we have a log of 1. What's log of 1? 0. So we actually have an indeterminate product. And from here, we're only one step away from an indeterminate fraction. In this case, it's really easy. So we take the limit. So the log of this whole thing stays where it is. And instead of cotangent, I say 1 over tangent. Right? It's the same thing. So now we have a fraction. What is the tangent of 0? Is 0. So we have a 0 over 0 indeterminate fraction, which is ready for us to use the L'Hopital's rule. Questions? So limit. See, the function on top is a composite function. So we have to use the chain rule to differentiate it, right? So I have 1 over this whole thing, sine 2x, times the derivative of what's in the brackets. That's 2 cosine 2x. And in the denominator, I have to differentiate the tangent. I have 1 over cos squared x. Okay. So let's simplify this. This guy goes to 1. Okay. Oh, actually, I don't even have to simplify. Sorry. So let's look at each term separately. So the sine disappears. I have 1 here. So this whole thing is 1. Cosine goes to 1. I have 2 here. This goes to 1. So everybody goes to 1. And I have a multiplier 2 here. So that's the answer. But I'm not quite done yet, because this is not the original limit. This is the limit of the log of this expression. So to find the original one, to find the limit of sine 2x cot x, we use the fact that we know the log of this, right? So we have the limit as x goes to minus of e to the y. So this guy is equal to e to the y. And this is e to the limit as x goes to of y. And we just calculated this. So it's e to the 2. So this is one step that separates the L'Hopital limit from the original one. You just have to raise it back to, you have to use exponentiation to get rid of the log. So first to do the log, do all the dirty work there, and then raise the answer, raise e to the power of the answer that we received. Okay. Questions? We're going to do one more example. So what's the limit as x goes to 0 plus of x to the 5x? So x goes to 0, and so does 5x. So this is a clear example of the first type of indeterminate powers. And the method is the same. For all of these, the method is the same. We say y equals x to 5x. And then we take the log. Log y is 5x log x. And so let's calculate the limit as x goes to 0 plus of 5x log x. This goes to 0, and the log goes to minus infinity. So we have an indeterminate product, as always in these examples. And as the next step, we turn that into, so 0 times infinity. We have to turn this into an indeterminate fraction. So we leave the log exactly where it is, and 5, 2, and we divide by 1 over x. Is everybody clear how to turn a product into a fraction? So we take one of the terms and invert it and divide by it. So now the log goes to infinity, and 1 over x goes to infinity. So we have a nice indeterminate fraction. And we are ready to differentiate in accordance with L'Hopital's rule. So we have 5 times 1 over x. Okay. And next we invert. And this gives me the answer of 0. But this is not the final answer yet. This is the limit of log of y. Okay, so the limit at x goes to 0 of y is the limit of e to the log of y. Okay, so it's e to the 0, which is 1. So who won? This guy won, right? This guy wants to make the power to 1. Thank you very much.